series. My name's Thomas Lumley. I'm a professor in the Department of Statistics, and it's my pleasure to introduce the series for 2021. This is the 5th year of the Ihaka Lectures, which was started in 2017 to recognise the contributions of Ross Ihaka to the field of statistics. The lectures broadly cover research in statistical computing and its application to science and society. As you probably know, Ross, together with Robert Gentleman, developed an environment for statistical computing and graphics called R. In the 1990s, they made this system freely available to the world and then allowed a group of people they knew only through email to meddle with it. For example, I was a graduate student in Seattle at the time. With the help of a steadily growing community, R has become the lingua franca of statistics. Its availability has made a sophisticated range of modern statistical methods available to a wider range of research and application than ever before. It has also allowed a wide range of people interested in statistics to develop programming skills and confidence to create their own tools, a statistical environment that does contain user-serviceable parts. The Central CRAN software repository, for example, hosts packages written by about 10,000 different people. Ross has now retired, but the Department of Statistics continues to advocate for the importance of computing in statistics and also for the importance of statistics in computing and data science. This year we have 3 lectures across that full range of topics. Today, Simon Urbanek from our department will talk about research in collaborative statistical computing. Next week, Rima Vaithianathan from the AUT Centre for Social Analytics will tell us about using machine learning to support decision-making in child welfare. And finally, Rochelle Binney from Manaki Whenua Landcare will describe the modelling of COVID that she and her colleagues at Te Punaha Matatini did to support New Zealand's COVID response. I hope you will find these lecture series enjoyable and educational, and I'll get Iro to welcome today's speaker.
Kia ora koutou. So my name is Iro. It's my great pleasure to introduce our first speaker for the Ihaka lecture series tonight, Dr. Simon Urbanek. So Simon and I both studied at University of Auckland in early 2020. Luckily, we made the move to New Zealand before the border closed. And we both have the honor of winning the prestigious John Chambers Prize despite many years apart. Simon has spent most of his careers at the famous AT&T research labs working in data science and artificial intelligence for the past 15 years. And I had the honor of meeting Simon in 2017 at the NZSA conference in Auckland. He presented his work on R Cloud, a social coding environment for big data analytics. After that, it seems Simon fell in love with New Zealand. So 3 years later, he decided to join University of Auckland as a senior lecturer. This is enabling him to pursue his research interests in statistical computing and graphics. So Simon is a member of R Core and the author of many R packages. And many of us have used Simon's R contribution in our own work or taken any inspirations from his work. So now I'm going to head over to Simon talking about data science in the connected era.
Thank you. Thank you very much, Iro. So, kia ora koutou katoa. I'm very honored to be here, so I'm glad that I can stand here and try to share some knowledge. I really decided normally I'm first creating the talk and then I'm thinking what the title should be. But really this time I figured I'll turn it around. I think about what I really want to talk about and then try to evolve around that. So really what I want to talk about is data science and how that relates to our modern connected era, and especially how all the changes that happen up to this point are enabling us to actually leverage all this new technology and knowledge as data scientists. So that's sort of roughly what I want to talk about. And of course it will feature rCloud as well, but I want to sort of frame this in a more general way. And the takeaway that I want people to take from this is more sort of the general ideas. And of course we can provide tools, but it should inform our practice as data scientists as well. So what is data science? This is a good question. I figured I'm just going to put it out here since it's the beginning of the title of my talk. And I used the Data Science Association definition, which says data science means the scientific study of the creation, validation, and transformation of data to create meaning. Sounds reasonable. Data scientist means a professional who uses scientific methods to liberate and create meaning from raw data. So very interesting. So the focus is starting from data. What can we do with it? And the focus is on liberation, meaning there's something hidden in there that really we want to use and create meaning from it. And historically, people have been doing that for a very long time. So the concept itself is not really new. What's new is more the technology and other things. So if you think about it, how people have used data, have they collected data in order to extract meaning from it, and that has been true for many, many hundred years actually. People have been studying movements of planets, recording them and trying to figure out how that works. And as an example, just because my background was in visualization, I figured I'm just show one example, which is visualizations from 1786, which is from William Playfair, where he was essentially trying to extract the meaning from the data he had. In this case, it was just the volume of exports and imports of Scotland. He was trying to show it in a graphic to try to understand how can we extract information from this. So it was sort of one of early days of creating graphics out of data in order to extract meaning. And this was obviously a time when people were doing all of this by hand. So all we had was just paper, pen, trying to draw things. So the real revolution came essentially with computing. Sometimes it's actually noted that someone who has mentioned the concepts of data science long before the term data science was coined was John Tukey. So at Bell Labs, he wrote this really interesting article, it's called The Future of Data Analysis. So he didn't call it data science, he called it essentially data analysis, where he was kind of frustrated with the current situation of how the fields of mathematics and statistics are handling things, and thought that there is something new coming and was trying to put that in words. So, the quote from the article here is that says that he felt that my central interest is in data analysis, which I take to include, among other things, procedures for analyzing data, techniques for interpreting the results of such procedures, ways of planning the gathering of data to make its analysis easier, more precise, or more accurate, and all the machinery and results of mathematical statistics which apply to analyzing data. So you may recognize some of the keywords here. So things like interpretation, so it's all about meaning. What can we extract as a meaning from the data? How do we gather it? So it's not only about just trying to getting something and trying, so it's how can we collect the data in such a way that we can extract the meaning from it, and then make the analysis easier and more accurate. So sort of very similar to what we see today as data science, where we're gathering data and even trying to extract meaning out of it, in a similar way that by applying procedures, so procedures essentially we can say code these days, as well as applying mathematical statistics and similar fields. So it was really a cross disciplinary idea that we should really be getting out of just single strands and just try to include everything in there. And there's a couple of quotes from the same article, which again, I just want to sort of bring them in perspective to a real data science. So, I would say that for the, last 15 years when I was working at AT&T, most of what we've been doing was trying to analyze data and extract information out of it, maybe inform whether it was the business or for urban planning or any other purposes that were interesting. We were just trying to extract a meaning from the data and then maybe have actionable items. So one of the points he was making was the data analysis must progress by approximate answers at best. So this is sort of in a context where previously everything had to be sort of very precise and trying to exactly model something, but really in these days, approximate answers are usually good enough because you just don't have the time and or the data is so messy that approximate answers are good enough and for the application, for the meaning that is out of it. The data analysis must seek scope for usefulness rather than security. So again, the focus is on what's the meaning, what can we do with it, what can we do, how can we change our operation to, let's say, based on what we see in the data. And we should seek wholly new questions to be answered. So we just don't use the old tools or old methods blindly. We want to see if there is something else that we could do, even if it's maybe quick and dirty, but the main thing is, does it really apply to the situation here? And finally, an interesting thought was, if sophisticated data analysts are to gain depth and power, they must have both the time and the stimulation to try out new procedures of analysis. Hence, the known procedures must be made easy for them to apply as possible, meaning we want to collect what we have in such a way that we can apply it in the future. So just having some methods is not enough. We want to make sure that they are now available for people to come so that they can develop their own methods and add to the knowledge base that we have. And we have to remember that all this was written before the advent of computing, really, at the time. So this was in 1962, and here is sort of a little bit of the timeline, mostly focused on what are relevant events in the computing from the 60s to today. So way back in the 60s, computers were really just available for a select few in some institutions, and were as big as half of this room. So an example is here. So it was not really available to everyone to use. It just started being applied. So of course tools didn't exist. So those things had to be developed. So Unix started. Then in the 60s, we have the first, let's say, truly data analytics / data science tool, which was S, which was essentially a way of taking the knowledge we had, which were algorithms that existed, and being able to apply them to data at the time. Now, very cumbersome, but still applicable at the time. Then the sort of personal computer revolution came, so that computers were no longer only accessible to select institutions. People were able to buy computers, use them for different purposes. It wasn't necessarily the start of the data science for everyone yet, because computers were really used for most other purposes than, let's say, data analysis most of the time. However, technology started developing. So for example, in the late 80s, we have the first sort of parallel frameworks which allow to scale the computational abilities of people to sort of clusters of workstations and things like that. And then we have R that came about, as Thomas was mentioning earlier, which really made it possible for other people. It being an open source project was actually very important, because that meant other people were now able to use it and contribute to the system. And that was one of the key aspects which I think we should take as important also for the whole field of data science. So next evolution was that we got the internet. So people started connecting not only just computers, so up till then, there were ways to connect, let's say, big machines, but it was not a way that you could communicate among more people. It was essentially just a way to exchange individual pieces of information. And with the internet and the advent of web technologies, we do see the rise of cluster computing. Hadoop was created, which meant now we can scale things, so we can deal with much larger data sets than we could before. We can write new methodologies. We have to think about how do we change them from the way we used to do it before now to this parallel world. And also, more importantly, technologies like the idea of moving from your own desktop. So here on the left-hand side, we have big in your rooms computers. You had to go there to use the computer. The middle, we have machines. Everyone has a machine around here. Whereas now we're able to shift all that to essentially a point where I no longer need to have direct access to the machine. I just need to use it. However, from a data science point of view, is it really useful? How can we leverage that? And I'm listing just some interesting concepts because I'll use it later on, which is things like WebSockets. That means web technology had to develop. So before that, we could communicate between computers, but for people, that was not really useful. It wasn't until we had browsers that we could actually see other pages, but they were static in the beginning. It wasn't until we get WebSockets that now we can really communicate with your computers or systems at such a rate as if we were sitting in front of them. And I'm also mentioning GitHub because the advent of distributed repositories and the whole idea that things are now no longer centralized in some place, but just are out there and we use them. We don't actually even care where they are. We need them. We just use them for the services they provide. You don't use them for the actual infrastructure. And so here at the bottom, I want to sort of point that out, that we went from sort of individual use to a world where now we have a lot more people using the technology, all the way to a point where we have now social networks. So people are communicating with each other all the time, and there are some issues that are associated with that, but as a principle, it means that we can leverage that technology without even thinking about it. So the question is, how does that relate to data science? How can we leverage those technologies as data scientists? So here comes my connected era part. So what does sort of our modern connected era really mean? So one thing is that we are decoupling the users and the infrastructure. So in the previous days, you had your computer, that's what you used. You were sitting in front of it. We had a lot of software that you could use. For example, for visualization is a good example where we had a lot of software that was just working on an individual computer, and the moment you were someplace else, you couldn't use it. You could only use it at a computer. However, today, where the computer actually is doesn't really matter to you as a user for most of the use cases that we know. And of course, web technologies were instrumental because without it, we couldn't really do this shift from single computers to remote access. So that means you were just able to, let's say, connect to one particular machine through some specialized protocol, all the way to cloud computing, where now we can just run things somewhere and we don't even know where the machines are. The other part of the connected era is that we have instantaneous access. So that means previously we had to own the resources in order to do something. Now there is the ability to just say, I just want to access those resources. That doesn't mean I need to own it. I can just use it and I can leverage it. The next one is location independence, which goes with it. Of course, once you get from remote to cloud, it doesn't really matter where you are. You don't have to be in the same building. Obviously, we are trading connectivity for location. So that means if the connectivity is not good enough, then that limits your ability as well. So it's not completely a free gain here. But as long as you can maintain good connectivity, then this is available to you. And so my last point here is really that data science was not really the primary adopter here. And I would claim that in part it's because we lacked the tools. So we do have tools that we can run on individual computers, We have, and that's about it. So most of the tools we have are good at leveraging your machine. So you can sit with your laptop, but that's where it ends. It doesn't involve anyone else. It doesn't allow you to extend things to other computers, even to the cloud or whatever amorphous thing it is. So what I'm trying to see is how can we leverage those abilities that we have today for data science. One more quote from Juntuki here. Most data analysis is going to be done by people who are not sophisticated data analysts and who have very limited time. If you do not provide them tools, the data will be even less studied. So this is something that, where's Chris Wilde, is preaching for years now, right? So he talks about democratization of data and data analysis, and has been developing insight for many years now, with the idea that we want to push the barrier and see if you provide people the tools and you make it simple enough, they'll be able to extract information from data, essentially becoming data scientists by the definition that we've seen, just by the virtue of giving them the tools that they can do it. So Insight's doing that in sort of a way where by giving people software that this can be done. And I'm saying we can push this even further, and if we combine this democratization of data, with the scale that we have of leveraging the connected era methodology, we're even expanding this even more than we did so far. So just a quick word on sharing. So one thing about data analysis, as I'm trying to point out, it shouldn't be something that you do on your own, just isolated. It's something that you want to share with others, because the more we share, the more we can leverage the work of others, and the more we can collect the amount of tools that we have so that other people don't need to reinvent the wheel. As we said in the earlier quote, it was give people the tools for the things we know so that they can develop what we don't know, or that's new. So that's the idea. So what did we do so far? Obviously, journals were the primary source of information and sharing before computers and all that. Then with the internet, that meant you could actually make things available on your website. So some people did. There is plenty of code out there where people just publish their own code. Sort of also, this is connected to open source, very important, as we said earlier. R wouldn't be the success it is if it wasn't open source. So people were just giving other people code and ideas so that they could replicate it. But it was limited because it was just whatever the code was, you could download it, but that was about it. Then came the web repository, so that meant central places where people could come. So with the simple web pages, it was just a matter how do you find that information, so that you'd have to know somehow that this thing exists. Whereas with web repositories such as CRAN, it meant that now people agreed we know where to find that information. So if I'm looking for a sort of cutting-edge statistical methodology, there's a high probability that I will find an implementation on CRAN. So that made a huge difference. So suddenly we were able to not only disseminate the methodology by the ways of such as journals, we're actually able to replicate what other people did, didn't have to code it ourselves. We could just take the package and apply it to our data. So that was very, and again, I would claim that was one of the big advantages of R, because that meant that people were sharing knowledge through the system, which means people had even more incentive of using the system because they knew they can develop new technologies and be on the cutting edge with this system, even though there were many other competitors and other systems, so especially in the commercial space. So finally, from web repositories, we moved to essentially version-controlled collaborative repositories. So GitHub is a good example because version control was there before, web was there before, but it wasn't until people started using it, the interface was so nice that people just started using the system and everyone started coming to the same place, that it really took off. And that's, of course, originally it was all intended for code. So open source projects was also free. It did help as well, or is still free, were then coming to GitHub. So the question again is, could we leverage something like that for things more than just code? So the answer is really yes, and some people are starting to do that. So I have just a couple examples here, which I found were really fascinating, because GitHub was really originally a place where you would associate with open source. But when the COVID pandemic hit, New York Times just created a GitHub page where they were updating and collating data from all over the world, trying to, well, actually from the US, sorry. We get to the world, sorry. But they were collating because it was such a mess that they were trying to find one place where they could just publish this information in real time as they're trying to process the data. And the second one is actually, that's the worldwide one. So there is another repository that now does the same thing for the entire world. So now the nice thing is that you can actually go out there. So this was the New York Times, or is the COVID-19 New York Times repository, and it gets sort of updated. You can see 2 hours ago was the last update. This is the one by Our World in Data. So this one also updated 2 hours ago. So now we're getting to a point where these things can be updated in real time and can be used as a shareable resource by other people. So now we're getting to sort of the point that I was trying to see, where there would be the ideal situation of trying to leverage the capabilities we have so that we can do this. So, so the point I want to make here is that most of this was used for methods, especially journals and so on, then code, sometimes data, but actually rarely analyses. So far we've covered methodology. So if we have a new methodology, we can put it out there, create a package. There are packages that have data or that can be published on GitHub. But if you do some kind of analysis, it's actually more rare. It still exists, but it's more rare. And one example that I just stumbled on just recently, because we were, actually this was just talking about the fact that sharing, even in our beautiful Aotearoa, we do have, actually our government is using GitHub and trying to disseminate data, code and data using GitHub. So for example, the New Zealand COVID Tracer app is on GitHub, so you can just download it, you can look at it. But another example that I wanted to make where analyses are actually being published is, for example, Traffic Calmer. I just happened to talk to the Ministry of Transportation, and we started talking about a project, and they were pointing out that there is this analysis that has been done for the UK, and could we transport that and apply it here? And part of the problem is that it's nice, there are nice results, and they have really good, for example, they have really nice analyses and write-ups of what they did. But if you dig deeper, you can say, oh, there is actually a source code, so you can try to replicate it, but only partial part of the analysis is actually available there. So it's a good start. That's sort of where we want to go. We want to be able to take this and then, let's say, apply it to our country. So for that, we need a good way of being able to replicate what the other team did and then apply it in our case. So that is really part of the main issue here. So we need to be able to reproduce what the other analyses did. And that tends to be harder than we think. I mean, reproducibility has been the topic of discussion for several years. I mean, people are trying to with things like, Markdown or R Markdown and other things, sort of trying to come up with technologies where we can share information, but it still hasn't quite caught up to be a sort of commonplace in the application. So, how are we giving time? Just to see how does this relate to the data scientific process. So I just want to quickly go over this. Essentially, we as statisticians are very familiar with this piece, so we're able to create models, fit models, look at it, and so on. Speaking of looking, then visualization is the next step, so we need tools to be able to do visualization. R has been really good at those pieces. But in modern analyses, there is this whole area where we need to get the data, we need to clean it, process it, transform it, maybe join it with other data sources. And there is no one good tool, because it depends on the things like where does the data live? Is it structured, unstructured? Is it just some logs we need to process? So there's a whole set of tools that you may need to use. So this one makes this reproducibility so much harder, because if I have similar data set, it doesn't mean that I can just blindly apply the same chain in order to get my analysis. And of course, at the end of this, we want to communicate the results. So fortunately, again, with the web technologies, we're now able to do that. And there is rise with all packages like HTML widgets and Shiny and so on allows us to do this, or even just our Markdown. So we have tools there. But the other argument I would make is that it's not just about the little pieces, it's also about people. So not always do we have one single person responsible for all of this. As we saw earlier with the model of sitting in front of just one computer and doing everything yourself, you can be much more powerful if you can leverage the work of others as well, not just what you're doing. For example, the knowledge about a data set. It could be experts that know a lot more about a subject matter, a lot more about the issues with the data. Because, again, as we were talking about tools, we want to be able to use tools such that this process is seamless. So that's kind of the dream, that we want to have collaboration, reuse, reproducibility, so that the work that we do can be shared with others, can be leveraged by others, and that way we can go forward. So it gets even more complicated in real life, because it may not be just one process. There may be multiple different data sets from other people that you want to join. And maybe in the end of the day, you want to deploy this as some service for someone. That has been sort of rise in, let's say, college dashboards recently, so that people now are trying to really visualize things and give it to people so that they can drill down themselves. Again, more towards the democratization, which is a good thing, but that requires different skill set and tools. So here's my wish list. So what if we push the data and analytics sort of in the cloud? So we want to leverage the modern connected era technology so that I don't have to care about where and how, meaning what's the infrastructure itself, the machines, let's say. And I want to be able just to go to the system and I write the code, maybe using R or whatever language I'm comfortable with. And also I want to have the users that will then look at my results to come into the same system so that I don't have to switch systems or create static outputs. So both consumption and development is sort of in the cloud. That also solves the scalability. If we can detach these two things, that means if someone has a lot of resources, has a lot of money, they can just buy a lot of VMs and run things, and it's fine. If they don't, it's fine. You can just run it on small scale. It's all possible. Automatic version control, this comes more from the necessities of creating, when you're working on any kind of data analysis, you don't want to lose your work, and you also want to see what has changed, and maybe, especially if you're working with other people, trying to find out how can, what has changed so that we can work together and see what did I add, what did the other person add. And everything should be web-based so that we can access it from everywhere. And also, as a side effect, that means the visualization piece is now much more powerful because we can use web-based visualizations, which are now sprouting, from not necessarily from statistics, but from information visualization and so on as well. So at the end, it's the sharing and collaboration that I want to sort of make as a centerpiece. So as one implementation, and I'm not saying this is the only one, but it's the one that we came up with at the labs for ourselves as data scientists, is R Cloud. So I just want to show a little bit of R Cloud. So essentially, in the beginning, it's just a web-based system, so you just use a browser, so you don't care where it really is. And you can just run your regular code. So, for example, let me see how we're doing time-wise, if I can try and do the full analysis here. So let's say we want to download this data set. So because I'm lazy, I'm just going to say, okay, let's just use shell and just download the data set. All right, now I'm in R, so I can just say, and I want to spend less time, so I just use IOTools for it to be faster. But so I have a CSV file, so I can read the CSV file here. Oh, thank you. I was wondering, why is it not completing, right? I shouldn't write R in a shell cell, yeah. So, yeah, the support for multiple languages has its drawbacks, but anyway, so that's what oh, did I get an error instead here? Promise I did try it before, but so let's just see if this does. Oh, this is not, I suppose this is not the raw link. All right, let me see if they actually have the complete data set. So let's try this. That looks better. That looks better. Okay. Oh, I'm back in the shell. Okay, let me change the language to R right away here. All right, so we can look at the data set, and sure enough, we have all the observations here. It essentially has the countries as well as the dates, and there's a bunch of variables that are associated here. Most of them have to do with total cases, new cases, there's some smoothing, there's even things about ICU admissions, hospitalizations, vaccinations. So it's a really, really interesting data set, as well as some statistics from the countries themselves. So you can, it's actually a nice and rich data set so that you can try to play with it. But because I'm just trying to do something really quick, so what I'll do is first thing I do is I have to say that our date is actually a date. So just hope that I'm not going to, and then maybe I'll subset the data set. So there is this ISO code. And in fact, they introduce not only individual countries, but they have statistics by continents and also complete world statistics, so essentially just aggregated. So just for the quickness here, I'm just going to extract that one. So now I can do things like I can look at the date and the, let's say the new cases.
You want E, Simon?
Oh, thank you. It'd be better if I also saw better. Mm-hmm. And hopefully, sure enough, we'll see our plot, which is based on the latest data that we have available here. Now, one of the points so far is like, oh yeah, I could have done that in a regular R session just using my computer, which is true. But the whole point is really that everything you do is automatically version controlled. So you can look here, and this is the history of all the things that I've done so far. So you can go back to any point and just revert to that point or and compare it. The other thing is that you can just click on the button here, which essentially gives you a shareable URL that you can send to anyone else. And they don't necessarily need, if you don't want to, they don't even need to have an account. And essentially just redoes the analysis, so they can go there, can look at the results. So this is more, obviously, when you did some more complex analysis. You can send it to people, and not only can they look at it, they can also click here and say, oh, I actually want to edit this, I want to change this, and they can do that. So right now, in this case, because it is my notebook, then I just get straight to the notebook. But if it was someone else's, you could fork it and start working on it. And at that point, you can compare things like what did you do compared to the other person, and you could merge it back if you need to. So everything is essentially version control using Git. So all the tools that you would expect are at your disposal, such as merges, comparisons, and so on. So that's one aspect. The other one is, so we encourage collaboration. So everything you do by default is public. So people can search for other people's work. So I can go and I can say, okay, I would like to know something. I mean, are there any scripts that have to do with Hadoop? Because I want to leverage, let's say, the Hadoop system. So we can look here and I can see, oh, there is something here. So I can look at it and say, oh, okay, so this is a shell script that tells me how to run a Hadoop job, but maybe I'm more interested in something that's R-based. So maybe I go in here and say, oh, okay, so now I can look at this, and if it wasn't, again, I can just click on run, and I can just run the script. So in this case, I can just see what happens. And sure enough, if I start this, it actually starts a Hadoop job that goes to the cluster, start processing the data. And then at some point, we will be able to read the data in, and I can see that further, once the data is processed, I can read it in, do some kind of visualizations. In this case, what this job really does is, if you look in here, what it does a point polygon test based on shapefiles and just returns the polygons that the counts per polygon by calling the table function and then just reducing it across all the polygons. And so when I read it in, now I'm reading it from the Hadoop file system, and I'll see it's essentially just the polygon IDs and the counts. So I can just, in this case, it turns out it's New York City. It's the New York City taxicab data. And I can also leverage interactive visualizations such as JavaScript. So in this case, I can use Leaflet to use an interactive visualization. So this is the benefit of being in a web-based system. I'm not restricted to just, let's say, regular R graphics devices. I can leverage JavaScript and interactive graphics as well. So this is sort of, the idea is that you can discover other people's work. You can look for other people's work, and you can run it. You can just go there and run it, see what it does, and you can learn from it. You can modify it to make it fit for your application. So if I see someone's analysis and I have a similar data set, let's say I have the same kind of model that I would like to apply, I can just search for it and then I can apply it and modify the code. So first I will see how it actually works in the other person's case, and then I can start modifying it. In addition, you're not limited to just code. You can also include additional information such as scripts or files or anything like that that you want, and it's also version control, so it's automatic. As you saw with my issues with switching the right language, we do support, in this case, multiple languages. The shell was one of the examples, but maybe more realistically, we do support Python, Python 2, Python 3. In fact, anything that has a Jupyter kernel is supported. So if there is a kernel, you can use it. And maybe I'll risk it and try to find just do a simple Python example. So in this case, I'm just obviously using something simple, but even things like graphics and things like that work as well, depending on, regardless of sort of the language that you use. So this was just a quick demo of what is possible. There is an entire architecture that I won't go in detail into. The only thing I want to mention here is that the whole idea here is that we create a platform that can be deployed or in many different ways, depending what the needs are. You can be running all of this on a single laptop. You can be running it on a huge cluster. It's completely scalable because of the separation of location. So, the user can be on the same system. It can be the user can be absolutely on a different continent. In fact, this instance I was using right now is actually in Auckland, just to make things faster and simple. But we have an instance that's running on Amazon in the US and anywhere. It doesn't matter really where you deploy it. And that's the idea is that we want to separate the piece of infrastructure from the user, so that let the system administrators worry about things like, how many machines do you need? How many machines do you want to pay for? Or do you just want to use, let's say, AWS, so you just, or any kind of cloud computing, so that you will just pay for whatever capacity you need, because you only need it maybe for a short period of time. So you don't need to buy the hardware. It's just, should be easy to just scale it up and down depending on what you need. I won't go into the implementation details. The only thing that what I was mentioning now is essentially there are many different ways to use the platform itself. So it's sometimes it's a little confusing, because when people say cloud, some people mean that's the service. So let's say if you use iCloud, then it's the service that's meant here, because you're just saying, oh, I just want to offload the files over there, or Google Drive, or whatever it is. But sometimes cloud is the actual infrastructure. So let's say like AWS or Azure or anything like that. So that's the infrastructure. So I just want to make sort of the distinction here, so that from the user's perspective, it should feel like cloud, but that doesn't mean that you have to use cloud as the infrastructure. You can have it on your machine or your university network. Visualization is a plus. That was sort of a nice side effect in all of this. That meant we can now leverage all the JavaScript libraries, all the visualization libraries that are out there. And that's why I think this is important for me as someone coming from interactive graphics background, is that means we have developed all these statistical interactive graphics over the years, but they were all tied to a particular system. They were first, everything was, let's say, on a Mac operating system. Then it was written in Java. And then now we can actually do it. If we do it using the web technologies, then we know this will be usable in the same manner that what I was describing here, which was not the case with anything we did so far. So it's something we can do and continue building. So back to our picture with that process. There are other open source tools that do similar things, so I just wanted to mention them, and for just very quick sort of historical comparison. So Jupyter started about the same time as we did with our cloud. We were focusing really on the collaborative aspect, and that was our main goal. Jupyter started mostly focusing on the sort of single user, splitting them later into kernels and that kind of aspect. And then later on, they started adding the sort of the collaboration features. Similar with our studio, it started as just one little, as a software that's just running on a single computer. And then because it was inherently web-based, it was sort of easy to put it on a server, but then there was no collaboration, and now they're trying to add these things as well. So in the end, what I really want is I want to essentially leave you with this idea that data science can benefit hugely from the modern technology. So the whole introduction that may have been quite long, the whole point was I was trying to make, how did we get from the technologies that were developed over the ages to this sort of fast-paced, connected era where we have cloud computing, social networks. And I think we can leverage those technologies for our purpose, so that we can, as statisticians and data scientists, we can share our work, we can share our methodologies, we can also share our analyses, and that way open that to other people that can leverage that. And I think especially, I'm really glad that here in Aotearoa we do have several entities, especially government entities, that do open data, are willing to collaborate, publish things. So we should publish methodologies, we should publish analyses, we should publish code. So we should be trying to sort of use those technologies in our favor, or really for everyone's benefit. So collaboration and sharing is important. That's what I personally believe. And from all those years that we've been using our cloud, so we developed it for ourselves, We were using it ourselves for all our analyses at AT&T. It was a central tool, and the sharing was really the big win there, because then we could leverage each other's code, and it worked really well in that respect. So the decoupling of the user data and compute means we are much more flexible. We can do things we couldn't do before otherwise, and it's up really to the users or administrators at some point to sort of see how much do you want to throw at this problem. And as I said, web-based technologies are very good for interactive visualization. And I was just showing our cloud as an example that it is possible. It's not just a theory. And we wrote it for ourselves. We deployed it in a large organization. It's all open source, and it's based on Ross's legacy. So it's our cloud for a reason. We started, of course, we were the major users of R, and R really allowed us to build this really flexible and versatile system because of the foundation of R. And the possibilities that we could extend it the way we needed it. And we later on added the support, let's say, for Jupyter Notebooks, but that's really just a little add-on. Really, the core came from R and the R thinking as a data analytic tool. So let's share and collaborate. It's my final word here. So not just code, but also analysis. Let's just share the knowledge, and hopefully we can have the tools to do that. So thank you. It's just...
Please wait for me to bring you a microphone. We're being recorded.
Thank you for sharing your vision and for a gripping talk, Shimon. Many analyses are commercially, contractually, ethically, culturally sensitive, not just the data, but the analyses. Is there any benefit that can be garnered for these types of analyses from web-based platforms, or are we condemned to keep them in the past?
Yeah, thank you, Alan. So it's a very good point. I would actually make the case this approach is exactly very good for those cases, because what it means, you can isolate the cases. That means you can provide, let's say, a sandbox for the cases where you have a sensitive data and you need people to collaborate on this data. You can have control over what you're exposing. One of the nice things, which I was mentioning here directly as a technical side, is there is, technically speaking, one single port in and out of the system. So you have full control, you have full logging, you know exactly who did what. So that makes it really good for cases where you need to have control over what happens and make sure that things are secure. So even though I'm advocating for sharing, the platform actually is also really good for applications where you do need to have full control over what you allow and whom you allow the access to. And also actually allows you to join things where you have maybe different users that do need to collaborate on data, but may not necessarily see each other's work. So we do fully support encryption. There is group keys, there are personal keys, there's all what you would expect that allows you to have fine-grained control. And that's, in fact, we talked about use cases, for example, taking the Maori data sovereignty into account, because that is exactly what I'm trying to say, because it means you can set up these systems in such a way that you could grant access based on who's eligible to get access and guarantee that that access is really provided and it's not leaking out data or information. So, in fact, even though this was conceived as a sort of sharing platform completely open, it can be restricted either by the way you deploy it or even by using encryption and other methods. Any other questions?
Along the same vein, in terms of sharing and making sure that things follow a standard, if you have, for example, a core set of standards that are to be adhered to, is there, in your version control, you mentioned keys and encryption, is using something like the blockchain in order to compare against that standard and have a majority of people compare to it to make sure it's correct? Is something like that in the cards as
So
well?
we don't have any blockchain in the system. However, the way the system is designed is that there is never any arbitrary code execution. The way the system works is that in order to do anything, what happens is you first submit the code. It has to get into the repository. So essentially it has to get into the system first. It gets recorded, then it can be executed. So that means by the virtue of essentially using the version control, you have full sort of traceability of what has happened. And also, if you wanted to, you could plug in some kind of checking. I'm not sure that is necessarily the best place to put it. That would be a long talk about, whether can you guarantee safety just by looking at the code that's being executed. I believe that's a very complicated question, actually. But the system, in principle, allows you to sort of trace every single step and be able to control that if you need to, if you have some methodology. So we don't implement anything ourselves, but we do have an API that essentially everything has to get through before it gets executed. So you could plug in something like that.
More questions?
I recall a couple of years ago, Ross gave a lecture on how he would have engineered R differently, in particular to address some performance issues. It seems that with this approach, you're essentially brute forcing all those issues away, and they kind of become irrelevant. Is that the case?
So the question was about performance. So several things here. So one is that people were saying, oh, R is slow. It's mostly has to do with the fact that everything had to be in memory. However, that has been sort of broken recently by either just developing more new methodologies where you're essentially just saying, okay, I'm creating references and I don't have to have things directly in memory. There's been the alt-rep representation in R that has been introduced, which means you can actually create new representations of objects in R that are not based on the same way that R used to represent it. But even pragmatically, I must say that we've been using R at AT&T to analyze data sets that were in hundreds of terabyte sizes. We were using it on clusters. So if you know what you're doing, then it really can scale to very, very high scale. And also, obviously, if you throw enough computing at it. So that's the brute forcing aspect that you're referring to. I must say that was less of the issue because the code itself, like if you run any kind of modeling, it actually is very performant in R. And also, there has been a lot of progress in the last few years with Tomáš Kalibera and Jan Vitek, among other people, with the help of Luke Tierney, have been tweaking and optimizing a lot of the internals of R. So a lot of things that maybe used to be less efficient are much more efficient today. To a point when I'm teaching Stat 782 here about R and performance, I have to always update my lectures because if I give an example of, oh, this is really inefficient, don't do that, you run it in modern R and actually it runs fast. So, so yes, so these things R still evolves. So even though a lot of the decisions are sort of locked in place with respect to the API that R uses to talk to packages, but some of the implementation can be changed and are being updated as we go. Any more questions?
Let's have to do the last one.
The idea of the interconnectivity twigs in my mind the problem of getting instructions as to how to do things. I'm a slow learner, and what your example you just gave, having to revise your lectures all the time, kind of harks back to this. That if I want to use something, I can search around, do a web search, and I find some information about it. But as somebody said recently on our help, there's a very bad signal-to-noise ratio, and there's correct instructions out there, and there are out-of-date instructions. And
absolutely. So
this is a huge problem.
I fully
learning how to use R Cloud or how to use GitHub you've got to get the instructions, and you've got to get the right instructions and not out of date ones, and it seems a terrible problem to me.
So I fully agree, Ralph. I mean, it's true, and I find the same thing, that the signal to noise ratio has been kind of getting worse and worse with respect to finding things on the internet, and that's why sort of one way here is that by essentially having these environments that are shared by the people that are working on, and whether it's in a similar company environment, university, you're limiting it from the entire internet, maybe. So that may help, because then you know what other people are doing. Now, it sort of slightly defeats the purpose of what I was saying. So what I was saying, we should share everything. It definitely is a problem, but at least in a way that as people are posting to these social media and so on, there's very little sort of control and blogs or whatever where you find information. But we still do have channels like mailing lists or the canonical sources. So something similar would have to happen. Essentially, you have your environments that you trust. And I don't think, at this point at least, I don't think that this would devolve to this sort of wild west or whatever it would be of disinformation on our cloud, hopefully. So in that sense, that's why I'm trying to say that I want to present it as a platform. So you choose who will be the people that you want to collaborate with and how you want to deploy it. So I wouldn't necessarily yet, at least, advocate for having like one center place where all the models of the world do accumulate. So we still would have to rely on some way of sort of exchanging things. And in fact, our cloud allows for multiple sort of repositories of notebooks, essentially. What it means is that you can say, okay, if my organization has an instance and your organization has an instance, I can actually allow your organization to search in and pull in the notebooks. They may or may not run because the environment may be different. So that's the big if there. But at least that gives you sort of the way of expanding the horizon as much as you think is safe. So that would be sort of, that's all I can offer.
Right, we have two last things. First, we have a small gift for Simon. Well, thank him for... Aha. Right, and the last thing is a quick draw for T-shirts, like this one. So there are two simple rules. One, you have to have registered for this session, and two, you have to be here. Okay? If you satisfy those two things, then you are eligible for the draw that is about to happen. Now, this is just me on a single machine, and this is just an R graphics device. But is that person here?
No.
How do you know that you're not here? Oh, okay. So that's an example of invalid attendance. All right. No, all right. Is that mispronounced? Misspelled? Is that person here? Speak quickly. False alarm. Oh, no, okay, it's okay. No one has to go anywhere. The third rule is we actually don't have any T-shirts. What we need... But actually, could you write down for me this name before I lose it in a second? So what we need you to do is, can you email the stats department with your T-shirt size, and we will get one for you. Is that all right? How's your patience? We want to do another one. No, all right. Oh, okay. Second, please write down David Robertson. Robertson? Awesome, thank you.
I'm trying to figure out why my registration didn't come up on my card. That was
Excellent, all right. There we go. 2 free T-shirts. Okay, and the final bit of news, of course, is that next week we have another speaker, Rema, and so I hope to see some of you here then. Thanks again, Simon.